So today we're going to be covering another topic in separation processes in chemical engineering, and that is the Ponchon-Savarit diagram. Now, previously we worked with a McCabe-Thiele diagram where we used kind of a staircasing method between the rectifying and the stripping sections to determine the number of stages that we can have in a distillation column and mess around with what our recovery, our reflux ratio, and all sorts of different parameters, how that affects that diagram. The Ponchon-Savarit diagram works in a very similar way, where we're still focused on basically this basic distillation column that I kind of just drew up. We have a condenser up at the top. We have a distillate leaving that condensing stage. We have our vapor and liquid flow rates. And for right now, I've just drawn out these few stages, but really what I'm going to be focused on is kind of here. And the goal of this video is going to be proving the theory behind a Ponchon-Savarit diagram, proving through method of similar triangles how we can use difference points to determine the vapor and liquid mole fractions within each stage in a distillation column. And the first step is going to be deriving some mass and energy balances. So let me start here with the energy balance. So let's look at what is leaving and what is entering in this system here. Really, I should be drawing that distillate more like it's a leaving our system. Something like that. So let's look at how we want to do the nomenclature for this here, right? So of course we have a vapor and a liquid flow stream here, and we have a distillate flow stream here. We also have this Q cooling that is being I guess kind of fed into our system, you could say. It's being used to take that vapor back into the liquid form to then be used throughout the distillation column. Some of that will be distillate, some of that will be liquid, determined by the reflux ratio. That's stuff that we've gone over. So in terms of what is entering, I'm going to say that we have a QC over here. So we have that rate of cooling. And then we're going to have that vapor coming from the stage below. So this is a vapor flow rate coming from the stage below. So N plus 1. And then we also want to, in terms of getting this in energy terms, we want to calculate the vapor, the enthalpy of that vapor from that stage N plus 1. So these are the things that are entering our system. Now, in terms of what is leaving our system, we are going to have our distillate. So that's going to be our distillate flow rate times the enthalpy of our distillate, plus this liquid stream that is leaving. So that's going to be from stage N, not N plus 1. It's coming from the stage above. And also the liquid enthalpy of that stage, that stream leaving that stage. So quick little fix. Instead of on this side, our heat should actually be on the other side. So glad I caught myself there. This will be here. That cooling power. Right, so now we can do the mass balances as well. And the mass balance is going to be quite analogous to our energy balance, where instead of the enthalpies, we're going to be focused on the mole fractions, right? So again, we have that vapor flow rate entering from the bottom. So Vn plus 1, and then we're worried about the vapor mole fraction of that stream from that stage. Then we're going to have our distillate flow rate times that distillate liquid mole fraction plus our liquid flow rate from stage N, and then also that liquid mole composition from stage N. And there's no heat term involved there, so we're good. Also, what we can do is we can draw up an overall mass balance where we look solely in terms of the mass flow rates, right? So we have our vapor, we have our distillate, plus our liquid flow rate. So these are the basic mass and energy balances we'll be using to prove our similar triangle theory for our Ponchon-Savarit diagram. So now let's look at our other mass balance that we did it. We could go back through and we could go back and plug in and do the simplifications and all that. But remember, when we derived this mass balance, I had stated that these mass and energy balance are actually analogous to each other by term of whenever we have this HV, we have a Y term. So this vapor enthalpy turns into that vapor mole fraction. Where we had the enthalpy of the distillate, that was the mole fraction of the distillate. Wherever we had the enthalpy of the liquid, that was the mole fraction of our liquid, and we simply didn't really have a heating term there, or a cooling term in this case. So instead of running through that entire thing all over again, what we can say is that, well, since these are two analogous functions, let's just go ahead and rewrite this for the mass balance. So I'm going to say that this is our energy balance here, and then our mass balance is a similar equation. So we still have this ln over d term. Now what we have is we have our y n plus 1 term minus that x n term equals we didn't have this QC term anymore, so I don't have to transfer that down. This HD turns into our distillate mole fraction minus yn plus 1. So now we have these two analogous functions that are representative of our energy balance and our mass balance. And using this relationship, we can go ahead and start plotting out the straight lines for our stripping, or not our stripping, but our rectifying section, and prove why mathematically this Ponchon-Savarit diagram is designed in a way to allow us to find that vapor mole fraction based on the enthalpies. So now algebraically, the next most sensible step is we now have this new definition for this vapor flow rate. So why don't we go ahead and plug it in wherever else we see it. So I'll start with this energy balance, and trying to find a bit of room to do this, maybe down here. Let's see. All right. So now we'll say that instead of our Vn plus 1, we're going to put in this overall definition for it. So we're going to have a distillate plus our liquid flow rate from the stage above times our enthalpy of the vapor from the stage below, and the rest stays the same. So dHd plus L sub n HL comma n plus that cooling power that we had. And let's combine like terms here, right? So I'll multiply this out really quick. So d HV n plus 1 plus ln HV n plus 1 equals d times HD. You get the point. I think I'll get my liquid flow rates on this side, and I'll get my distillate flow rates on this side. That makes the most sense to me. So when we do that, we will pull out this Ln term, and it's going to be our vapor enthalpy minus our liquid enthalpy equals, and now we can pull out that distillate flow rate, and that's going to be our distillate enthalpy minus our vapor enthalpy plus that cooling power. Now, the last thing that I'm going to do here, and this is, I think I will also kind of rearrange it, but I'm going to divide everything by this distillate flow rate. So this will look like this. And then I'm going to actually flip-flop the order of this here. So I'm going to have QC over D. And then this will just be additive here. So plus HD minus HV and plus 1. So here is the simplified form that we were aiming for. And the reason that I kind of did it this way, and it'll just make things easier to point out later, is that this point here, and I'll write this in green just to match up, this is our difference point in the rectifying section. This QC over D plus HD. So this is our cooling power over the distillate flow rate plus the distillate enthalpy will give us the difference point in the rectifying section. And when we go back to the Ponchon-Savarit diagram, I'll show you just where this lies on that graph. But this is a very important piece to have in the back of our pocket. So to begin generating a Ponchon-Savarit diagram, we start, and I'll just choose this point at the very end. We start at our distillate liquid mole fraction. So this point correlates with this first vapor mole fraction. And then above it is where we find that difference point I was talking about earlier. This definition here. That's what we have. So in the Ponchon-Savarit diagram, what ends up happening is that we start drawing these lines. And these lines this first line starts at the difference point, goes through our Y1, and essentially what that will bring about is that we will also have, so let's say this is over here, right there. So let's say this is our X1. So this is the liquid mole fraction of that first stage. We take a ruler, draw a line connecting that point to the difference point, and then this intersection point here is defined as Y2. So what justifies us being able to draw this straight line and allowing us to determine the vapor compositions based off of this criteria? So we would want to point our attention towards, we have a triangle that comes up around here-ish. Let's say right here. Come on, draw straight. Doesn't want to draw a straight line, but let's just say there. Should be more of a straight line here, though. There. So the difference between this X point here and this X point here, if we go back, so this is essentially our X1 minus our Y2. So if we look over here, there is that difference point over here. So the difference between our Y and our X from the stage above. So this is our X from the stage above. This is our Y from the stage below. So that's where this piece comes in here, and we can write that. We can write that out. So I guess I'll use this color. This is yn plus 1 minus xn. So now, what about this y component of the triangle? So that is actually the difference in our vapor enthalpy and our liquid enthalpy. And like how we pulled this vapor mole fraction and this liquid mole fraction, it's analogous to this difference in the enthalpies. So one side of this is the mass balance, the other side of this is the energy balance, and you'll see that pattern reemerge when we do the second set of this. So I'll do something like, I wish I had more room here. Maybe I'll go like this. This is HVN plus 1 minus HLN right there. Cool. So now, what about this other triangle we've got going on here? And let me use a different color to make it a bit easier to read. But we also have so we also have the other side of this equation here, right? We have this delta D minus HVN plus 1. We have this XD minus YN plus 1. So let's start with our mass component just to follow suit. So right here. So this first point here, this is XD. This here is XD, right? So at this point, y1 equals xd, and if you remember the McKay-Thiele diagram, this is something that we have done a postulate for, and similarly, using these mass balances, we were able to prove that when we are at the distillate composition, our mole fractions are equal to each other. It falls on that 50-50 line. So similarly here now, we are worried about that stage above. So this, or sorry, not the stage above. I keep mixing that up. This is the stage below. So over here is where we have our distillate composition. So this is the stage from where we are pulling that vapor composition from. And so as such, we will call this difference point here this is going to be our XD minus YN plus 1. Right? Now, we will also examine the difference between this delta D point. So this is going to be delta D minus that vapor enthalpy from the stage below. And that is present right here. So all of this follows the the energy and mass balances that we derived earlier. And we can see now that through this postulate of similar triangles, that we have sort of proven that, yes, the straight line that goes across is defined by the differences in our enthalpies and the differences within our masses, our mole fractions. So this straight line that intersects at this point is recognizing the fact that this is where our vapor composition for the stage below is going to lie. So this is for the rectifying portion of the Ponchon-Savarit diagram. So now that we've covered that rectifying section, let's start working on the stripping section. So I've drawn up just a standard reboiler here, and we'll use this as our system. So first, for things that are entering our system. Now in this case, our heat, our reboiler heat over here is going to be part of entering our system, not leaving our system. So we can go ahead and we can say that our L, so this is going to be L from the stage above, yes, L from the stage above times enthalpy of that liquid stage above plus QB. I'll just say this is energy here, is going to be equal to that vapor from the stage below that's leaving our reboiler times the enthalpy of that same vapor from that stage plus our bottoms flow rate times the enthalpy of the bottoms. Okay, it's pretty good. The mass balance is very similar. This is, again, going to be analogous sort of to our energy balance, but remember that we also, in that stripping section, we have that feed. And that feed will also have a feed composition, so something like a Z that we are going to have entering our system, right? The rest of it is similar. So Ln Xn plus, we don't have a heat term anymore, that's gone. So now we also have a Vn plus 1 times our Yn plus 1 plus our bottoms times that bottom mole fraction. And then we also have whatever we are feeding into our system has to show up in our bottoms and our distillate. So whatever is entering our system has to also show up either at the top of our distillation column or at the bottom of our distillation column. So here is the energy and mass balance for that stripping section. So now, I actually don't love this mass balance here. I think we'll tackle that a different way. But so for now, let's just focus on this energy balance that we've got going on. So one thing that we can say is that, well, in terms of just strictly inflows and outflows, so we're going to have some liquid entering, and this has to be equal to the vapor leaving our stage and the bottoms. So let's go ahead and we can substitute this in. So this will go here. So we get something like Vn plus 1 plus B times that liquid enthalpy plus QB equals Vn plus 1 H V n plus 1 plus B HB. That's not what I wrote. I don't know why I did that. There. And then again, we will combine our terms. So we're going to have a Vn plus 1 times HL N, and then that's going to be, I think I will keep my vapor. Well, let's just see. Let's see how this works out, right? So Vn plus 1 HL N plus BHL times N, or that's like the liquid enthalpy. There, just write the rest of this down as it was. So now we have our vapor enthalpy, and I think I want to subtract my liquid enthalpy for that to make sense here. So I'll go, so this is going to be B liquid enthalpy minus bottoms enthalpy plus QB, so boiling heat. Move this over a bit. Equals, this is going to be Vn plus 1. This is going to be the vapor enthalpy minus the liquid enthalpy. And that went over there, so we're good here. I'm going to do the same thing as last time. I'm going to divide everything over by B. So now we have HLN minus HB plus QB. QB over, why is it doing that? There. Equals Vn plus 1 over B HVn plus 1 minus HLN. All right. So now what we have here is, remember when we defined this delta D term, now similarly what we have over here is actually our delta B term. So this here is going to be delta B, delta bottoms. Delta of the bottoms. And now I'm going to go ahead and pull my mass balance from this actually. Remember that last time when we did this, we had analogous equations for energy and mass balances. So I'm just following that same kind of ideology. So we have X from the end stage, and then we don't have this heat term here, but we still have our X at the bottoms. This stays the same, and then we are looking at the difference between our vapor mole fraction and our liquid mole fraction. So here we go. This is our energy and mass balance for the stripping section. So this is our energy, and that is for our mass. So let's go ahead and demonstrate the same thing for the stripping section now. I'll use here, this is going to be our delta B, and we'll draw this up, and remember that this delta B is at our bottoms composition. So this liquid and this vapor are both at this bottoms composition. So what ends up happening is that we will have so we're going to have this point intersection here. We're going to have this point intersection here, although we aren't terribly worried about that. We will have some point, let's say here, that'll give us a tie line. So this is a line, this point is going to be in equilibrium with this liquid composition, and this is going to give us this intersection point. Something like this. And then this will go off and repeat the process. You will find another tie line down here. Maybe say it is in equilibrium with this liquid composition here, and this liquid composition will go off and give you the next vapor composition. So here is your vapor composition. It'll happen probably one more time here, and then that's your liquid composition for the bottoms. Now, what is this idea of tie lines? Well, this is basically saying that this point here and this point here, these are two compositions that are in equilibrium with each other. And that's also present in our rectifying section too. So see, if you draw a tie line here, you find these 2 points are in equilibrium. You draw from your delta D point, you draw down to your liquid composition, and it gives you the next Y value. And then you go off and you say, well, what is the liquid composition that is in equilibrium with this Y composition? You'll go ahead and you'll find that point, and then you'll go ahead and draw another straight line, basically. And then you rinse and repeat this process over and over again. So then we will go back to this idea of having our similar triangles. So first let's go look at our mass balance. So this is going to be from our bottoms composition to this stage above. So this is our bottoms composition here. Here is our stage above. So I'm going to try and get over there. About there, I think is fine. And then where is the energy component? Well, that energy component is going to be from that bottoms composition to that liquid composition line, or that liquid enthalpy line. So the delta B over here up to this this liquid enthalpy line. So here's our first triangle. Then our next correlation is from that same liquid composition from the stage above to that vapor composition from the stage below. So if we go ahead and we try and find where that is, so here is that liquid composition that we are looking for. Here is that next vapor composition that we, or not this one, but rather this one is the one we want. So I'm going to say, like, it's coming down right about here. And then that last bit is going to take us from that liquid composition to the vapor composition. And that is shown right here. So this is the same postulate that we used to describe these similar triangles for the rectifying section. And you can see those same similar triangles being used to justify this line here to find our vapor compositions in our stripping section.